Okay, class, today we're going to move in a little different direction. So our topic today
Attention teachers, we are conducting a tardy exit period. Please shut and lock your doors at the final bell. Thank you.
is matrix solutions to linear systems. And our homework is section 8.1, page 893, numbers 13 through 20. So a matrix, it's a shortened way of writing a system of equations. So a matrix is a shortened way of writing a system of equations. An augmented matrix has a vertical bar separating the columns of a matrix into two groups. Where you have the coefficients on the left-hand side and the constants on the right. So coefficients on the left and our constants on the right. All right, so here's what I mean by that. So let's say we have a system that we dealt with in Unit 7 or Chapter 7. So let's say we have 3x plus y plus 2z, and that's equal 31. X plus y plus 2z equals 19, and x plus 3y plus 2z is equal to 25. So that's a typical system of equations that we dealt with last chapter. So this is our system. Now, if we were to rewrite this in augmented matrix form, to represent this system, it would be written as follows. So in our first row, you have 3x plus y plus 2z. So our coefficients would be 3, 1, and 2. Now we have a vertical bar. Our constant is 31. Our second equation of x plus y plus 2z equals 19, you have 1x, 1y, 2z. Our constant is 19. And our third equation of x plus 3y plus 2z is 25. You have 1x, 3y's, 2z's, and our constant is 25. So here is our augmented matrix to represent the system of equations that we started with. Now, what's the goal in using a matrix to solve a system? So our goal in using a matrix to solve a system is to get ones down the diagonal. So here, these terms here are the diagonals. So this 3, this 1, and this 2. So our goal is trying to get a 1 in those spots, the diagonal going from the upper left to the bottom right there of our variables. Now in row 2, there's already a 1 there, which is a neat thing. But in row 1 and row 3, there are not. So we're going to need to use some sort of operations to get ones in those spots. Now we're going to define another type of matrix. So take a look at this matrix here. So it will be a matrix that will have ones down the diagonal. So let's say this is 1, and then we have some A, B, and C. Then we have 0, 1, A, B, C, then this is D and E, and then 0, 0, 1, and then that's F. So here, we do have a 1, ones down the diagonal, but at the same time, underneath each of the ones, we have zeros, except for the last one because there's nothing underneath it. So a matrix with ones down the diagonal and zeros below the ones is in row echelon form. So again, a matrix that has ones down the diagonal, and the ones in the diagonal beneath those are zeros. This matrix is in row echelon form. Okay? So, let's talk about matrix row operations. So with our matrix row operations, number 1, 2 rows can be interchanged. We can interchange rows. Number 2, we can multiply a row by a non-zero number. And we did that when we were solving linear systems. If we needed to eliminate, let's say, a y, and we needed to multiply one row by -2, we did that. The only thing we couldn't do is multiply a row by 0. Okay, step 3. We can add the newly created row from step 2 to any other row. So for a matrix row operations, a lot of what we need to do can be done using one or more of these 3 kind of basic rules there. So let's take a look at an example. All right, so let's say we have this matrix, 3, 18, negative 12, and then 21. 1, 2, negative 3, and 5, and then negative 2, negative 3, 4, and negative 6. All right. So the first operation we want to perform, let's say we just want to switch row 1 with row 2. So what that will yield is row 2 now becomes row 1 now becomes row 2. So this is 1, 2, negative 3 and 5, 3, 18, negative 12, 21, and then negative 2, negative 3, 4, and negative 6. Okay. So that's just switching row 1 with row 2. Okay. Now let's take a look. And again, we're going back to the original, not the one that we just modified. So for B, let's say we wanted to take 1/3 of row 1. And again, we're doing this to the original, not to the one modified one. So 1/3 of row 1, well, every term in row 1, we're going to multiply it by 1/3. So that would be 1/3 of 3. Then we would have a 1/3 of 18, a 1/3 of negative 12, and a 1/3 of 21. Rows 2 and 3, they don't change at all. So that's still 1, 2, negative 3, and 5, negative 2, negative 3, 4, and negative 6. So our new matrix becomes 1/3 of 3 is 1, 1/3 of 18 is 6, 1/3 of negative 12 is negative 4, 1/3 of 21 is 7, then 1, 2, negative 3, 5, and then finally negative 2, negative 3, 4, and negative 6. Okay. And finally, let's take a look using the same matrix that we started with. This time, we're going to take a look at 2 times row 2 plus row 3. And really kind of focus on what exactly is being asked of us here. So 2 times row 2 and then adding that to row 3 means that we're going to add 2 times row 2 to row 3. And what this does is this will replace row 3. So we're going to take 2 times row 2, we're going to add that to row 3, and this is going to give us a new row 3. So this one I want to write it, I want to rewrite the original so we can see side by side what's actually happening mathematically there. Okay, so here's our original. So our original was 3, 18, negative 12, and then 21. 1, 2, negative 3, 5, and then negative 2, negative 3, 4, and negative 6. All right, so that'll go to. So rows 1 and 2 are going to remain the same, but we have 2 row 2 plus row 3. So 3, 18, negative 12, 21, 1, 2, negative 3, and 5. Okay, now let's perform the matrix operation here. So we're going to go 2 times row 2 plus row 3. So that means that's 2 times 1, which is 2, and then 2 plus a negative 2. So we're going to get a 0 in this spot here. 2 times 2 is 4. 4 minus 3 is 1. So again, 2 times row 2 plus row 3. 2 times negative 3 is negative 6. Negative 6 plus 4 is negative 2. And finally, 2 times 5 is 10. 10 minus 6 is 4. So at 2 times row 2 to row 3, replacing row 3. Okay. All right. Now let's take a look at using this, using the matrix, using these matrix operations to solve a system. Okay. So the method we're going to use is called the Gaussian elimination with a back substitution. So Gaussian, G-A-U-S-S-I-A-N, elimination. With back substitution. And so here's our system. 3x plus y plus 2z is 31. X plus y plus 2z is 19. And x plus 3y plus 2z is equal to 25. So that's our system. So the first thing we're going to do is we're going to rewrite this into an augmented matrix. So that becomes 3, 1, 2, and 31, 1, 1, 2, and 19, then 1, 3, 2, and 25. All right, and our goal is in row echelon, we want to get our diagonals equal to 1. And what I notice here is that in the upper left corner of our first equation, our first row, we have a 3 there. So one thing that we could do is we could swap out rows 1 and 2. And in doing so, row 2 now becomes row 1. So that's 1, 1, 2, and 19. Row 1 becomes row 2, 3, 1, 2, and 31. And then we didn't modify row 3 at all. So that remains as 1, 3, 2, and 25. Okay, now we have a 1 in the upper left-hand corner. Okay. Row echelon form, we need zeros underneath this 1. So here, if we multiplied this new row 1 by negative 3 and added it to row 2, then we would ensure that we have a 0 in that first spot. So this will go to, we're not going to change row 1, so that's 1, 1, 2, and 19. But row 2, we're going to go negative 3, row 1, plus row 2. Well, we also need a 0 in the first spot for row 3. So in that one, all we have to do here is just take negative row 1 plus row 3. Okay, so our new values are going to be, well, negative 3 row 1 plus row 2. Let's see, negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2. Negative 3 times 2 is negative 6. Negative 6 plus 2 is negative 4. And then negative 3 times 19 is negative 57. And negative 57 plus 31, I believe, is negative 26. Now, negative row 1 plus row 3. Negative 1 plus 1 is 0. Negative 1 plus 3 is a positive 2. Negative 2 plus 2 gives us 0. And then a negative 19 plus 25 gives us a positive 6. Okay. Now, we need a 1 in the diagonal here. So we have a 1 here, we need a 1 there, and a 1 there. So let's work on this one first. So here, in order to get a positive 1 in that spot there, we can just multiply negative 1/2 row 2. So row 1 doesn't change. 1, 1, 2, 19. Negative 1/2 of 0 is still 0. Negative 1/2 times negative 2 is positive 1. And negative 1/2 times negative 4 is a positive 2. And negative 1/2 times negative 26 is a positive 13. And we didn't do anything to row 3, so that still remains 0, 2, 0, and 6. Row echelon form. Now we need a 0 underneath this diagonal. So we need to make this 0 using row 2. So our next matrix, row 1 will remain the same. 1, 1, 2, 19. Row 2 remains the same. 0, 1, 2, 13. It's row 3. So with row 3, we're going to go negative 2, row 2, plus row 3. So negative 2 times 0 is 0. 0 plus 0, that remains 0. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Okay, negative 2 times 2 is a negative 4. Negative 4 plus 0 is a negative 4. And finally, negative 2 times 13 is a negative 26. Negative 26 plus 6 is a negative 20. Okay, we are almost done. Now, we need a 1 in this spot here. 1 across the diagonals. The only thing left for us to do is we can take row 3 and multiply it by negative 1/4. So negative 1/4 row 3. So we get 1, 1, 2, and 19. 0, 1, 2, and 13. And then finally, negative 1/4 times 0 is 0. Negative 1/4 times 0 is 0. Negative 1/4 times negative 4 is a positive 1. And then negative 20 divided by negative 4, or negative 1/4 times a negative 20, is a positive 5. And we are done. So what are our solutions? So here, coefficients, this is x, y, z. So you have x plus y plus 2z is 19. You get 0x, so we got y plus 2z is 13. And for our last one, x is 0, y is 0, you get z is equal 5. So remember, our goal is to solve for x, y, and z. So we already have one of our solutions. Z is equal to 5. Now this is called the Gaussian elimination with back substitution, because now you're going to back substitute this 5 to the equation prior. So we end up with y plus 2 times 5 is equal to 13. That's 10. 13 minus 10 is 3. You're going to get y equals 3. So now that we have z is equal to 5, y is equal to 3, we're going to back substitute those two into the first equation to solve for x. So x plus y, so x plus 3, plus 2 times z, so plus 2 times 5, is equal to 19. Here you have 10 plus 3, that's 13. Subtract 13 from both sides, and you're going to get x is equal to 6. So our solution is, to the linear system that we just solved using the Gaussian elimination method, our solution is x is 6, x is 6, y is 3, and z is 5. So that's the solution to the system. All right. Hope this helped you, and we will see you later.